Hello everyone. In the previous class, we were discussing the topic Fourier transform and Fourier series. In this video, we will discuss the various symmetry conditions for a periodic function ft. When a given periodic function is such that it possesses certain symmetry properties, then it is possible to tell by inspection what terms will be missing in its Fourier expansion. Also, the expressions for the Fourier coefficients of those terms that are present in the Fourier series can also be simplified. That is, certain symmetric conditions of the periodic function provides a shortcut for evaluating the Fourier coefficients as given in the following table. The given table shows 6 conditions of symmetry and their characteristic properties. From the given symmetry conditions, we can quickly find out the Fourier coefficients which will be present in the Fourier series, and the Fourier coefficients which will be missing in the Fourier series. Let us discuss all these symmetry conditions one by one. The first condition for symmetry is when a periodic function ft is equal to f of minus t, then the function will be an even function, and the characteristic property of an even function is that it will contain only cosine terms. That is, the Fourier series will contain only cosine terms. So, the value of Bn will be equal to 0 and the value of a0 by 2 will be equal to the average value of the function over a period t. The value of an will be equal to 4 by t integration 0 to t by 2 of ft cos n omega t into dt. And an example of this type of function is as shown in the figure 1. Here we find that A is the amplitude. Here we find that A is the amplitude of this function. A is the amplitude of this function, and we also find that f of t will be equal to f of minus t. So, directly by seeing this condition, we will know that this function will not contain the Fourier coefficient Bn. So, we will substitute Bn is equal to 0 and we will find a0 by 2 and an using these two formulas, and by substituting the values of these Fourier coefficients, we can find out the Fourier series directly. The second condition for symmetry of a periodic function is if it satisfies this condition, that is, if f of t is minus f of minus t, then in that case the function will be an odd function, and an odd function will contain only sine terms. This means that the value of the Fourier coefficients a0 by 2 and an will be equal to 0. So, we will directly substitute these two values 0. If we find if the function is an odd function, then we will substitute these two values equal to 0 and we will find only the value of the Fourier coefficient Bn using this formula, that is Bn is equal to 4 by t integration 0 to t by 2 of ft sin n omega t dt. And an example of this type of function is shown in this figure. From this figure we find that f of t will be equal to minus f of minus t. So, this function is an odd function, and so it will contain only the term Fourier series of this function will contain only the term Bn, and the coefficients a0 by 2 and an will be 0. So, we will directly substitute the value of a0 by 2 and an 0 in the Fourier series of this type of function, and we will calculate only the value of Bn in this case. Similarly, the third condition of symmetry is that if the value of the function ft will be equal to f of t plus minus nt by 2, n odd only, if this condition is satisfied, then the function will contain only even harmonics, both sine and cosine terms will be present. So, the value of a0 by 2 will be equal to the average value of ft over a period. The value of an will be given by this formula, 4 by t integral 0 to t by 2 of ft cos n omega t dt. The value of bn will also be found out with using this formula, and the example of such type of function is given in this figure. From this figure we find that f of t will be equal to f of t plus nt by 2, also that is equal to f of t minus nt by 2. This is the time period, this is the amplitude, this is minus of t. So, in this case we will have to find out all the 3 Fourier coefficients using the formula as shown in the table. Now, the fourth condition for symmetry is that if f of t is minus f of t plus minus nt by 2, then the function will contain only odd harmonics, both sine and cosine terms will be present. In this case, the coefficient a0 by 2 will be 0. So, we will directly substitute the value of a0 by 2 is equal to 0. If we find that this condition is satisfied, we will directly substitute this value equal to 0 without calculating the value of a0 by 2. We will substitute the value of a0 by 2 equal to 0, and we will find out only the value of an using this formula and bn using this formula. An example of such type of function is shown in this figure. From this figure we find that the value of f of t will be equal to minus of f of t plus nt by 2, and that is also equal to minus of f t minus nt by 2. This is the time period, this is the amplitude, and it satisfies the condition that f of t is equal to minus f of t plus minus nt by 2. So, in this case the coefficient a0 by 2 will be 0, and we will only calculate the value of the coefficients an and bn in this case, and by substituting all these values in the Fourier series we will find the Fourier series of this periodic function. Now, the fifth condition is when both the first and the third conditions are satisfied, that is if f of t is equal to f of minus t and f of t is also equal to f of t plus minus nt by 2 for n odd only. Means this function will satisfy both these conditions, both the first and the third condition will be satisfied in this case. Then this type of function will contain only even harmonics and only cosine terms. So, bn will be 0 in this case because the function will contain only cosine terms. So, we will have to calculate only the value of a0 by 2, which will be equal to the average value of ft over a period, and the value of an in this case will be equal to 8 by t integration 0 to t by 4 of ft cos n omega t into dt, and because this function contains only cosine terms, so the value of bn will be substituted as 0. An example of such type of function which satisfies both the conditions, that is if f of t is minus f of minus t and also f of t is equal to f of t plus minus nt by 2 is shown in this figure. So, in this case we will have to find out only a0 by 2 and an, and we will substitute the value of bn is equal to 0 directly in the Fourier series of such type of function without calculating the value of bn. Now, the last condition for symmetry is that f of t is equal to minus f of minus t and f of t is equal to minus f of t plus minus nt by 2 for all odd n. That is, in this case the conditions second and fourth conditions, both the conditions are satisfied, then in that case the function will have only odd harmonics and only sine terms will be present in the Fourier series of such type of function. That is, the Fourier series of such a type of periodic function will contain only odd harmonics and only sine terms. This means that the value of an will be 0, the value of a0 by 2 will also be 0. So, we need not calculate the value of a0 by 2 and an in this case. If this condition is satisfied, then we will not calculate the value of a0 by 2 and an, We will directly calculate the value of Bn using this formula, that is Bn will be equal to 8 by T integration 0 to T by 4 of Ft sin n omega t dt. And an example of such a type of function is shown in this figure. From here we find that this is the time period and this is the amplitude, and for this periodic function we find that both the conditions are satisfied, that is f of t is equal to minus f of minus t and f of t is also equal to minus of f t plus minus n t by 2. And so this type of function will contain only odd harmonics and it will contain only sine terms. So we will calculate only the value of Bn in this case. So by seeing the symmetry conditions, we found out that how easily we can find out the Fourier series of the given function just by inspecting the symmetry conditions for the given periodic function. I hope this topic is clear to all of you.